very much for the opportunity. So I will try to recycle a set of slides that were presented during a NanoSafe conference about 2 weeks ago. So this presentation is about EC2S project. So EC2S stands for Innovative Environmental Control System, Control Secondary System. It is a project in the Clean Sky 2 framework, and the ambition is to design an air circulation system that provides a multi-technology air treatment system for particulate matter, VOCs, and CO2. And so you have here the 4 partners of the project: CEA, Hutchinson, Ecologic Sense, and Terra Group. The idea of the project is to reduce the fuel consumption by lowering the bleed air flow rate. And to do so, the recirculated airflow has to be increased and filtered to keep acceptable air renewal rate and air quality in the cabin. The EC2S air management system addresses three kinds of air pollutants: VOCs, CO2, and particulate matter. And here is a schematic flow diagram of the foreseen system. So you have firstly the particle filtration part, which is performed by electrostatic precipitation. Then the VOCs, which is handled by photocatalytic oxidation. And lastly, the CO2 removal, which is carried out by amine-based adsorption. So a bypass is implemented in order for the CO2 filter in order to regenerate it periodically. And regarding the particle filtration, electrostatic precipitation has been selected as a potential candidate to replace or eventually complement filtration media, mechanical filtration media. So the main advantage is that electrostatic precipitation can provide, as compared to mechanical filtration, is a very low pressure drop, and the regeneration of the system can be just performed by cleaning the collection plates. So I'm working on the particle filtration part, so I will go in more details on this part. So here is presented the general principle of the electrostatic precipitation. In this configuration, incoming particles are charged using unipolar ions, which are produced by corona discharge. So the corona discharge is obtained by applying a strong non-uniform electric field on curved electrodes. And then we have the collection stage, where a potential difference is applied between metal plates so that the charged particles are attracted and collected on those plates. For the EC2S project, the performances targeted are listed here in this table. Mainly a flow rate of 540 cubic meter per hour, collection efficiency higher than 90%, and the pressure drop below 10 Pascal. So here is the electrostatic precipitation design strategy that we implemented in the project. So we started with theoretical calculation and simulation, and based on that, we manufactured a lab scale device that we tested, and using those results, we designed a full scale prototype. And so this prototype is being evaluated. And at the end of the project, the prototype, together with the other filtration unit for CO2 and VOC, will be tested in a cabin section demonstrator. So regarding, I will give you some results of the lab scale electrostatic precipitator. So it was designed to be working at the same airspeed as the final full-size prototype for comparison, and its performances were assessed in a wind tunnel setup to get the single pass efficiency and the ozone generation rate. So here I present some of the results obtained using potassium chloride aerosol challenge. So this aerosol presents a number-based mode at about 60 nanometers, and particle size distribution ranges from 20 to 300 nanometers. And so the influence of operation conditions, which are the corona currents on the charging stage and the voltage applied at the collection stage, were assessed. We demonstrated that for this lab scale unit, for optimum parameters, an overall efficiency of over 90% can be achieved. So additionally, we also used the platinum aerosol to challenge the lab scale prototype. So this aerosol, as presented here, comprises very small particles ranging from 10 to 30 nanometers. And you have on the right-hand side the results obtained in terms of efficiency as a function of the aerosol particle size. So in red, you have the data obtained with the platinum aerosol, and in green, the data obtained with the potassium chloride. And as predicted by theory, the minimum efficiency is observed at about 250 nanometers. More interestingly, we also demonstrated a drop in efficiency for particles with a diameter lower than 30 nanometers. So additionally, we also assessed the unwanted ozone generation of the electrostatic precipitator device. And we showed that the ozone generation rate is directly proportional to the corona current applied. And we also demonstrated that an optimum current range has to be applied to get the maximum efficiency while lowering the ozone generation. So using those results, we performed some basic mass balance calculation to predict the impact of the electrostatic precipitator prototype on the cabin air quality. So firstly, for the ozone generation, assuming a 65% air recirculation rate in the cabin, we calculated that in the worst case scenario, the ozone concentration in the cabin will not increase more than 25 parts per billion due to the electrostatic precipitator. And we also compared the influence of the electrostatic precipitator with an assumed 90% efficiency as compared to an EPA filter with a 99.9% efficiency. And for 65% air recirculation rates and assuming a constant particle concentration outside the aircraft, for example, on the ground, for instance, we calculated that the EPA would lead to a 65% decrease in particle concentration, which has to be compared to a 62.5% decrease in the case of the electrostatic precipitator. So using all those results, we designed the full-scale electrostatic prototype, electrostatic precipitator prototype, and we started to manufacture it, and we already started to assess its performances. And the preliminary results are quite encouraging and in good agreement with what we expected. They are presented here, and we are like the collection efficiency over 90% for particles with 1 micron diameter. Ozone generation lower than what we expected, and very low pressure drop at 4 Pascal. So just to conclude, we have successfully designed a full-scale electrostatic precipitator with a single-pass efficiency higher than 90% and low pressure drop and limited ozone generation rates. We are now working on optimizing the charging stage to improve the charging efficiency and lower the ozone generation. For that, we explore 2 approaches. The first one is to heat up the corona wire by Joule effect. And the second one is an alternative charging state design using carbon fiber brushes. And so after those optimization at the end of the project, it is planned to test the electrostatic precipitator together with the CO2 and VOC devices in a recirculation chamber, and finally in a real world environment in a cabin section demonstrator. So yeah, on that, that's it for me. So if you have any questions, I will be happy to try